Hello everyone. So today let's discuss the Johnson's algorithm, right? So one advantage of Johnson's algorithm is we can just brush up this one, Bellman-Ford algorithm along with the Dijkstra's algorithm. So Johnson's algorithm uses Bellman-Ford algorithm and the Dijkstra's algorithm as well within uh, uh, within the Johnson's algorithm, right? So one thing previously we had discussed on the Floyd-Warshall algorithm, and now we are discussing the Johnson's algorithm. So we have the knowledge on the Floyd-Warshall, and Bellman-Ford and Dijkstra's will have a brush up here, right? So we'll brush up the same thing within the Johnson's algorithm. So these five algorithms, whatever, we'll be finishing it off today, right? So next we'll be going with there are so many algorithms left, actually around 20 algorithms we'll be discussing, but let me tell you, to find the shortest path, right, these five algorithms are very important one. Yeah, starting with the DFS and BFS, that's completely primary, right? Primary in the sense that those are DFS and BFS, that's the basic, actually you have to know at any cost, right? So followed by this one, Dijkstra, Bellman-Ford, Floyd-Warshall, as well as the Johnson's algorithm. These are very important. You have to know this one at any cost, right? So yeah, let's start with the definition part here. Johnson's algorithm is used to find the shortest paths between all the pairs of vertices in a weighted directed graph, right? Again, Johnson's algorithm is used to find the shortest paths between all the pairs of the vertices in a weighted correct this one directed graph. It efficiently combines Bellman-Ford algorithm and the Dijkstra's algorithm to handle the graphs with negative edge weights. It efficiently combines Bellman-Ford and the Dijkstra's algorithm to handle the graphs with negative edge weights, but without negative cycles, right? So graphs with the negative edge weights, but without negative cycles. Let's move on with the explanation part. Now, first point here would be Johnson's algorithm works in three main steps, right? Johnson's algorithm works in three main steps. The first step here would be we will be adding the new vertex q. It's completely new vertex. Will be not kind of dummy vertex, but we'll be adding the new vertex q connected to all other vertices with a edge weight 0, right? This is very important. Just try to remember this. The same thing will be implementing in the form of code as well, right? Just remember this. We'll be adding a new vertex connected to all the vertices with the edge weight 0. Next, what we will be doing, we have to run the Bellman-Ford from Q to detect the negative weight cycles and to compute the A, right? So to detect the negative weight cycles and to compute the A, right? So here potential function h of v that run weight edges run weights edges so that all the edges weights become non-negative. So become non-negative. This part is very important. Now what we will be doing, so we have to, or we will be running the Dijkstra's algorithm from each vertex using the reweighted edges to find the shortest path efficiently, right? So we will eliminate, in simple terms, we'll be eliminating the non-negative edges, negative edges, sorry, and then we will be running the this one, what do we call Dijkstra's algorithm, because it finds this one. So we can make use of only the positive weights within the Dijkstra's algorithm, right? So then only we'll be able to find the shortest path when we make use of the Dijkstra's algorithm. Basically, it uses the priority queue, as I've said, right? That is one of the fastest, right? Among these algorithms, Dijkstra's is one of the fastest, right? So this is fine. Finally, we adjust the distance back to the original weights using the potential difference, right? So this is what we will be doing. So this one you have to remember. So we will be making use of Bellman-Ford as well as the Dijkstra within the Johnsons. So finally, I found this important, this point very important as well. I just wanted to discuss this one. So this algorithm is very efficient for the sparse graph, basically. This is nothing but the application. Sparse graphs, combining the flexibility of the this one Bellman-Ford as well as the speed of Dijkstra. As I mentioned, as Dijkstra uses priority queue, right? So that is faster, right? That's fastest, basically. That's fast or fast comparatively, comparing to this one, comparatively with the this one Johnson's, Floyd-Warshall, this one Bellman-Ford, right? So comparatively, Dijkstra is faster. Again, if suppose we know that we are making only this one, making use of the positive this one weights, then please go for the Dijkstra's rather than Bellman-Ford and the Floyd Warshall. I insist you to go with the Dijkstra's as it uses the priority queue, right? So this one you have to keep in mind. And when it comes to the Johnson's algorithm, so this is very efficient only for the sparse graphs, right? So this one I had to this one. What I'm stressing again. So this part is very important. So Johnson's algorithm is very efficient only for the sparse graphs, right? So this combines the flexibility of the Bellman-Ford as well as the speed of Dijkstra. Again, it is very efficient only for the sparse graphs, right? So um, if you remember the segment tree, Fenwick tree, and the this one, uh, sparse table, right? Sparse table had only a certain criteria, but only certain criteria of the problems we had to solve using the sparse table. So whatever sparse table can solve, that can be solved using the segment tree as well. But the code will be very smaller, right? The code will be very small compared to the code that we write in the segmented. That is the reason we make use of the this one sparse table at least. So this here that's tree based. That I just wanted to give you the this one example basically. Now whenever we are making use of the Johnson's algorithm, see, the code is lengthier as we'll be going with a combination of this will be three algorithms combined together, right? So basically Johnson's, Bellman-Ford as well as the Dijkstra, right? So code is lengthier and comparatively it's slower than the this one. What do we call Dijkstra, and it's slower than the Bellman-Ford as well. So yep, it's the only advantage of using the Johnson's algo is so it's very efficient for the sparse graph, right? So just remember this one. Now let's do one thing. Let's move on with the basically let's move on with the code or writing the algorithm, right? So first let me import heap as we'll be making use of the this one, right? Dextrous. So first step is let's go with the Bellman-Ford algorithm just to detect the negative cycles and to find the h of v, right? So I'll just go with def. Let me go with Bellman-Ford here. This is fine. Go with graph comma v, right? So this is fine, man. Now let's go with the distance equals, go with the float here, infinity. So this is fine. Up to v. Now let me go with the distance. This is fine. SRC. Let me assign this one to the 0. Now let's relax all the edges v minus 1 times. So that's what this one does, right? What do you call Bellman-Ford? Let's write this one very quickly. So I'll just consider underscore here. In range, just go with v minus 1. So this is fine. One more, two more for loops here. Bellman-Ford, three for loops, right? Nested for loops. So for u in range v and also for v comma w weights in the graph u h basically. Yep. Now within this for loops, so if distance of u plus w, so if it is less than the distance of v, then distance of v is equivalent to the distance of u of u plus w, right? So this is fine. Distance of u plus w, right? So this is fine. Now let's go with a one more for loop here. Let's check for the negative weight cycles as the Bellman-Ford is pretty famous for that itself, right? So for u in range here, this one v, this is fine. For v comma w, This one in graph, this is fine. So this one is U. Yep. Now within the two for loops, let me write the simple if condition here. If mm, distance of U less W here, if it is less than distance of V, then let's go with the print here. This is fine. Let me write something for the interactive purpose. So this one graph, behavior graph contains negative weight cycle, right? So this is relevant here. This is fine. Hmm, Next line, let me give here return none. Yep. Final one is let's return the distance. Yeah. Now, let me come out of this one entirely. Now we are done with the Bellman-Ford algorithm, right? So this is fine. Next, let's go with the Dijkstra's algorithm, right? So I'll just go with the here. Mm, so let me make use of the parameters graph as well as the src, nothing but the source here. This is fine. So let me assign v to vertex 2. So this one length of graph basically, right? So this one we have to do. Next, let's go with the distance. We know this one, right? So we have already discussed Dijkstra as well as the this one Bellman Ford, right? So this one will be float of let me pass infinity, yep, into this is so this one with into v. Yeah. Now let's go with the distance here. This one of let me pass source. Let me give you 0. This is fine, man. Now let's do one thing. Let me assign the priority queue to this one 0, comma source. Right. So this is fine, man. This is nothing but the distance, comma vertex. Right. So now let's go with the while of priority queue. So Dijkstra is famous for finding the positive with the positive weights, the graph with the positive weights basically. Right? So it uses the priority queue, we know. So now let me go with d comma u equals heap q dot. So we'll be going with a heap pop, right? So I'll just go with heap pop of the this one. Let's pass the priority queue pq variable. This is fine. Now, what if the distance is less greater than? So this I did the mistake while writing that distance as well. Distance of u, right? H u. Then we have to skip. So I'll just make use of the continue keyword here. So let me go with simple for loop here. V comma w in graph h, right? So this is fine. Next, within the for loop, what if the distance of u, if um distance of u plus w less than distance of I'll just go with a v, right? So this is fine. Distance of v, this is to distance of u plus w, right? So this is fine. Now let me go with the heap q or heap push, heap push. So let me go with priority queue pq and distance of v, comma, right? So this is fine. Yeah, I'll just come out of this one entirely. Now let's return something. I'll just go with return distance, right? So this is fine. Now let's do one thing. We are done with the Bellman-Ford as well as the Dijkstra. Now let's go with the or let's move on with the Johnson's algorithm, right? So this is fine. Let me do one thing. I'll just go with the def Johnson's algorithm. Yeah. So now let me pass here original graph as the parameter. This is fine. So within the Johnson's algorithm, same thing. Let me go with the let me assign the vertex to length of original graph. This is fine. The next path would be, let's add the new vertex connected to all the vertices with a weight 0. Meaning here, I'll just go with new graph here. This one, edges. So this is fine. Colon. What's wrong here? Why this is screaming? Edges is not defined. Yeah, let's do one thing. Here, we haven't written the code yet, right? So this one of edges basically. Let's consider, yeah, this is fine. For edges, not ed first one. This is edges in original graph, basically, right? So now we have to consider the new vertex as we had discussed in the this one. What do we call explanation? What we are doing here, we are adding a new vertex connected to all the vertices with weight 0. We have discussed this one in the explanation, right? So now let me go with the new graph again. Uh, let's append vertex here. Sorry, so this one, then this one has to be x comma 0. This is fine for v in the range. So let me pass v here. This is fine, man. Yeah. So something I have done wrong here, man. I don't know what I have done wrong here. So yeah, let me do one thing. Let me make use of the parenthesis here. Does this work? Yeah. This is working. This is fine. I hope this is correct. Now let's do one thing. Let's run the Bellman-Ford algorithm from the new vertex, right? Let's run Bellman-Ford from the new vertex. So this one will be Bellman-Ford. Let's pass the new graph here. So this one has to be vertex plus 1 along with the v, right? So this is fine. Now let's write the simple if condition here. If h is none here, if h is none, then what shall we do? Then let's return none here. Then let's return none. So this is fine. Now let's do one thing. Let's reweight all the edges using h of v, right? So this will be, I'll just consider the variable reweighted graph here, right? But just thinking of the variable name. So this is fine. Just consider empty array for score in. Let me go with the range v. Yep. Now let's go with a simple for loop here. For u in range v, then let's write one more for loop here. For v comma w and original graph. So this one, original graph u, then I'll just go with a reweighted graph of u dot append. So this is fine. V plus w h of u. So this is fine. Yeah. Minus h of v. Right. So this is fine. We are done with this part, I believe. So something I have done wrong again here. 1 second. Just give me a second here. End of v comma h of v. This has to be within the array, right? So this one is wrong. Then any other thing? No, I believe. Right? Yeah, this is fine. Now let's do one thing. Yeah, let's run the digistras for each vertex, right? Let's run the digistras from for each vertex. Right, so let me copy paste this one. Just give me a second here. So let me post some code here. So what we are doing here, so we are just running the digistras here, right? So from here, where just give me a second here, all pairs equals this one we have considered here, right? So this one from the line number 72. So we are just running the digistras for each vertex. And for loop for v whatever I have written, so here I have commented, we are just adjusting this one, adjusting the distances back to the original weights here, right? So we have considered the example graph here, directed this one from 0 to 1, weight 1, from 0 to 2. So you can just draw the graph, right? From 0 to 1, 0 to 2. So just keep the weight this one 1 from 0 to 1. From 2 we are going with a weight 4. From 1 to 2 we are going with a weight this one negative weight here -2, and then we are going with a positive two weights 2 and 3 for the edges 2 to 3 and 3 to 1, right? So graph this is shown here, right? Graph uh, I have shown here, right? So then what we are doing, so then we are calling the Johnson's algorithm here. Then we are calling the Johnson's algorithm here, right? Finally, we are going with a print statement here. All pairs shortest paths, right? So for I in the row, enumerate. So I have just written the this one from the vertex, a particular vertex. We are including this one row, right? So this is fine. Now the output that we need to get here is for this one, the output that we need to get here is this one. This one we have used, right? So this is the graph basically. Right? So yeah, 1 second. Just give me 1 second here. So the output that we need to get here is this one first we are printing all pairs shortest paths, right? So below that from the vertex 0 we need to get here as 0, 1, -1 and sorry, yeah, 0, 1, -1 as and 1, right? So this is fine. From the vertex 1, so we have to get here infinity 0, -2 as well as the 0, right? So this is also fine. From the vertex 2, we are going with infinity, this one 5, 0 as well as this one 2, right? So this is also fine. And finally, from the vertex 3, we are going with a infinity, this one 3, 1, 0, right? So this is just the this one. What do you call the output that we need to get here as this one basically, right? So why from the vertex 0 the shortest path to 1 here, the from the vertex 0 the shortest path to 1, so basically I'll just consider here from vertex 0 the shortest path to 1 is equal to 1 itself, right? For the from vertex 0 the shortest path to 2 is -1, this one through 1 to 2 basically, you can just check through 1 to 2. I can just write it over here. From this one, what do we call? From vertex 0, the shortest path to 3 is also 1 here, right? So this is via this one, the graph that we have considered from 1 to 2 to 3. You can just check, right? So this one, right? 1, -1 and 1, right? So 1, -1 and 1, right? So this we have completed. Now from the vertex 1, the shortest path to this one 2 is -2, 2 is -2 and 3 is 0, and 3 is 0, right? So this remains same, infinity and 0. And final this one via the path, this one what do we call 2 is -2, we know. For the 3 it is 0 via 2 to 3. You can just check this one 2 to, right? So we are left with vertex 2 and vertex 3, right? From vertex v2 from vertex 2, sorry, from vertex 2 the shortest path to 3 here is 2, right? And from the vertex to the shortest path to 3 is 2, and from 1 this one this is 5 basically, right? So it is via this one, what do we call 3 to 1, 3 to 1, right? So this is fine. Now from vertex v3, from vertex 3 or this one v3, as I'm considering this one v1 v2, so from the vertex 3 the shortest path to 1 is 3, 1 is 3. So this we are done, right? So this one from vertex 2 the shortest path to 3 is 2, this one, and 1 is 5. So these two things we are done with this row as well. The final row, let's come with this. From the vertex 3, the shortest path to 1 is 3. 1 is 3. This one. Yeah. Now from vertex 3, the shortest path to 2 is 1. 2 is 1. So this is via 1 to 2. You can just check this is via 1 to 2. You can just draw the this one graph and check. So this is via 1 to 2, right? So this one, right? So all the rows are completed here. So this is how we got the output 0, uh, 0, 1, minus 1, 1 for the first one, for the vertex 0. For the vertex 1, infinity 0, minus 2, 0. This is fine. For the vertex 2, infinity 5, 0, 2. And for the vertex 3, it is infinity 3, 1, 0. This one, right? So this is how we got the output, right? So let me run the code now. So I'll just come here, copy entire file name, give Control J here, clear screen. Let me go with, what shall I go with? Python followed by the file name dot py. We have some error man here. None type is not iterable. So line number h is h in none. If h is none, it has to be. So Johnson's algorithm, line number 64. Just give me a second here. One second. Yeah, number 64. If h, yeah, this has to be is actually not in. So let me give clear screen here. Let me run this one again, man. Again, we are getting error. So line number 51, cannot unpack non-iterable int object for v comma w in graph view. Line number 51. So what is wrong here? Again, for v comma w, it is correct itself for v comma w and graph view. Okay, for v comma w in the graph view. Yeah, for v comma w in graph view. This is fine if the distance of u plus w less than distance of v. Uh, 1 second. So basically in the Bellman-Ford algorithm, we have went with the wrong indentation right here. So this one we have to remove the return here. This is one of the things that is wrong. So now here within the Johnson's algorithm, so just let me come to the line number 70 here. So we have given reweighted graph of this one. This is fine. Fine. So v comma w. Oh, so this one I have to give comma here. So now does this run correctly? Let's check. Yeah, now this is running correctly. All pair shortest paths, right? So the output that we are getting here is, you can just pause the video and have a look into it. So you can just this one, rewind the video, right? So just go to the part where I showed the outputs. You can just check here. So we are getting 0, 1, minus 1, 1. This is correct. Infinity 0, minus 20, 0. For the vertex 1, this is correct. For the vertex 2, we have to get infinity 502. This is absolutely correct. And for the third one, for the vertex 3, this is infinity 310. This is also correct, right? So we are getting the desired output. We are getting the desired output, right? So this is it for the Johnson's algorithm. So these 5 algorithms are very important, man. DFS and BFS, Dijkstra's, Bellman-Ford, Floyd-Warshall, as well as the Johnson's algorithm. And one more thing, whenever you get a chance to implement, just try to implement the Dijkstra's rather than Bellman-Ford, this one, Floyd-Warshall, and the Johnson's algo. So that is faster as it uses the priority queue. And one more thing, if you're dealing with the positive weights, then only make use of the Dijkstra, or else you can just go with a Bellman-Ford. Suppose if you want to handle the negative cycles along with the negative weights, right? So then you can go with a Bellman-Ford. Only if you want to handle the positive, this one, positive edges as well as the negative positive weights as well as the negative weights, then you can go for the this one. What do you call Johnson's algorithm, right? Rather, and one more thing, only if you want to handle positive and negative, you can just go with this one as well. What do you call? Uh, uh, this one, Freud Warshall as well. That doesn't handle the this one negative cycle. right? So this one, Floyd-Warshall, right? So this is the difference I wanted to discuss. Now, let's do one thing. As we are done with the Johnson's algorithm, let me summarize whatever we have learned so far, right? So Johnson's algorithm smartly combines the Bellman-Ford algorithm just for handling the negative edges and the Dijistra's algorithm for efficiency on the non-negative, this one, weights, right? It smartly combines Bellman-Ford as well as the Dijistra's algorithm. Just remember, it runs in this one, Johnson's algorithm runs in big O of v square log v. Big O of v square log v plus this one, vertex and edge plus v. This is fine. So this is the time complexity of the this one, what do we call, Johnson's algorithm, because v square log v plus v time, right? So it is faster than the Floyd-Warshall for sparse graph. So this is faster than the Floyd-Warshall for the sparse graph. So again, I'm telling, so this is very helpful, or this is efficient for the sparse graph only, mostly, right? So sparse graph, whenever the problem is given on the sparse graph, then we have to implement certain thing, go for the this one, what do we call, Johnson's algorithm directly, right? It runs in because v square log v plus ve time complexity, time or the time basically, which is faster than the Floyd-Warshall for the sparse graphs, right? So I have given you the application as well. So when you have to implement this one, I have said that one as well for the sparse graphs, right? So this is faster than the Floyd-Warshall algorithm. So when it is ideal, it's ideal for the graphs with negative weights but not negative cycles. It's ideal. It is ideal for the graphs with negative weights but not the this one, negative cycles. We are done with the this one. What do you call? Uh, we are done with the Johnson's algorithm, right? So this is it for the Johnson's algorithm, right? Next, what we will be discussing, next we will be discussing the this one, Kruskal's algorithm and the Prince algorithm. Basically, next the next algorithm is going to be the Kruskal's algorithm, right? For the minimum spanning tree, right? So yeah, next we'll be discussing the Kruskal's algorithm. For now, we are done with the Johnson's algorithm. For now, this is it. Thanks for watching, guys.